All right. If you do have any questions, please unmute yourself and speak up, or send me a message in the lecture text channel on Discord. I didn't really get any questions before class, so I guess we'll jump right in and discuss the concepts for today. So last time we were talking about naming hydrocarbons, focusing on alkanes. So if you recall, we said the ANE suffix indicates a saturated hydrocarbon where there's no double or triple bonds. Find the longest chain of carbons. It might not all be spread out. I had a problem with that during lecture. So if I have, branching up here, my longest chain might not always be shown as a zigzag horizontally. I got to find the longest chain of carbons and then name the side groups. We'll be working with that naming system a lot this semester and next semester. So you really want to practice that up and get pretty good at it. We'll be using that discussion we had in the last lecture as our foundation, so that when we do start to look at molecules that have double or triple bonds, or halogens or oxygens or other functional groups, that we can expand the naming system to account for those types of situations. So today we want to talk about the structure three-dimensionally of some of these molecules and their energies or stabilities. So we got to talk about what energy and stability are really quick. If we want to assess the stability of a compound, there's experimental ways to do that. We can also look at the structures and try to judge stability. Obviously, any conclusions we make by looking at the structures would have to be confirmed experimentally before we can feel confident in them. But we also want to remember from general chemistry that if something is stable, it's low in potential energy, right? That's what stable means. It's not likely to react. It has a low reactivity. It doesn't have much potential for change because the particles present are already attracting strongly. So there's very little energy that could be released upon reacting if it's stable. It's low in potential energy. It doesn't have the potential to release energy. And that's because the particles present are arranged with strong attractions, or avoiding repulsions. So much in chemistry comes down to attractions and repulsions, as you've seen throughout your experiences. And that's what potential energy is all about, right? So generally, if we have two particles that have opposite charges, if they're close together, there's not much potential. It's stable because they're already nicely attracting. If I pull them apart a little bit, now there's more potential energy. As long as I don't pull them so far apart they can't experience any attraction, as long as they still have some degree of attraction, there's the potential for them to move closer together again. So as I pull particles that attract apart, farther and farther and farther, the potential energy increases until I reach a point where they're so far apart they don't feel an attraction together. And then at that point, continuing to pull them apart wouldn't change the potential energy. Likewise, if I had two particles that were the same charge, if I put them together, that would be high in potential energy, right? Because opposite like charges repel. So obviously, if they're right next to one another, there's a lot of potential. There's a potential for a change to occur in the positioning of the particles because of their current situation not being optimized with attractions and repulsions. So if they're right next to each other and they repel, they're going to be pushed apart. So those are simple situations, but they're more complicated situations where we're dealing with a reaction. And if you actually drove a car today or any time recently, the reaction that took place in there was a hydrocarbon reacting with oxygen. So that would be octane, is the main hydrocarbon in gasoline, and it has 8 carbons and 18 hydrogens. And when I react that with oxygen, it produces CO2 and water. So it's not a simple situation like we just have charged particles, but each of these compounds on the reactant side and the compounds on the product side involve atoms and electrons, and the electrons and atoms are arranged in space because of their attractions. So if all of the bonds on the reactant side are relatively stable, carbon-carbon bonds, the sigma bonds are stable, the carbon-hydrogen bonds are relatively stable, the oxygen bonds are not that stable. Oxygen bonding with oxygen creates a situation where these two highly electronegative atoms are both pulling the electrons away from the other, and so that's a relatively unstable molecule. We find oxygen much more often on Earth binds with hydrogen because the oxygen-hydrogen bond is a more stable situation where now the electrons can get nice and close to the nucleus that attracts them better. Not so easy to do that when both atoms are attracting the electrons evenly. And the carbon-oxygen double bond is a relatively stable bond as well, putting two pairs of electrons, one sigma bond, one pi bond. That's a relatively stable situation. So there's not a huge difference in stability between the reactants and the products here. Right? Both sides have complete noble gas configurations or octets for all the atoms. Both sides don't have any unstable formal charge. But sometimes just arranging the electrons in bonds differently makes those electrons more stable or lower in potential energy by allowing them to form stronger attractions. So in a combustion reaction, where I generally have some type of fuel that contains carbon and hydrogen, there may be other elements as well, reacting specifically with oxygen to produce CO2 and water as my specific products in a combustion reaction, that reaction goes from an unstable or high potential energy state to a more stable, lower potential energy state. And so that's a situation where, as we discussed in Gen Chem, if I'm looking at the enthalpy or potential energy or enthalpy versus the reaction progress, the reactants are higher in potential energy, the products are lower in potential energy. I always have to put some energy in to break the attractions that are there. There's an activation energy necessary, if you remember from Gen Chem. But that's not what heat of combustion is. If we're talking about the combustion reaction and the heat or the enthalpy change for a combustion reaction, we're talking about not how much energy you have to put in to get it to break up to produce a product, but after it produces the products, what's the difference in energy between the starting energy and the final energy? And if it goes down, that's a negative enthalpy change or release of energy because there is more energy to begin with and less energy in the end. And so that energy, that quantity of energy is released into the surroundings. So that basic understanding of potential energy allows us to run experiments and compare the stability of molecules. So we can compare molecules that have the same number of carbons and hydrogens. So if I have 1 mole of octane and I combust that, I can measure how much energy is released using a calorimeter. Right? We talked about that in Gen Chem. The quantity of energy released can be measured by looking at how much it causes the temperature of the calorimeter to increase as the reaction is releasing that energy into the surroundings, which is the calorimeter. I can take another molecule that's an isomer of octane. This one also has 8 carbons and 18 hydrogens. But when I burn this one, it doesn't release as much energy. And when I burn this one, it releases even less energy. So that tells me about the stability of these individual starting compounds. Right? So if it's releasing more energy upon combustion, it must have started at a higher energy, a higher enthalpy, or higher potential energy, so it must mean it was less stable. And I was looking at your quiz answers regarding this concept this morning, and it occurred to me that I didn't really understand exactly why this molecule is less stable than the other two. And what many of you were arguing in your quiz answers was that the one with more branching should be less stable. And that makes sense to me, because if I've got more branching, I've got these big electron clouds neighboring one another that start to repel, and that makes it unstable, right? Full electron orbitals getting close together are areas of negative and negative, and that repulsion makes things unstable. If it's all spread out, it should be more stable. So if you're thinking about steric hindrance, which is the repulsion between full electron clouds that makes a molecule unstable, that cannot be the explanation for what's happening here, because the one with more steric hindrance is actually more stable. So I was reading up on that a little bit, and it looks like the best current theory or hypothesis for that, which isn't necessarily maybe 100% accepted by organic chemists, so maybe some controversy there. The best idea that I could find was having to do with orbital overlap between bonding molecular orbitals and anti-bonding molecular orbitals. So we know that our bonding molecular orbitals are what create the sigma bonds. The anti-bonding molecular orbitals are all empty. So if I have a full bonding molecular orbital overlapping with a full bonding molecular orbital, that makes it unstable. That would make it higher in potential energy and give it the potential to release more energy upon combustion, or have a greater heat of combustion. So there's got to be something happening here. We're not going to get into detail with it, because it's really beyond the scope of the class, but it appears that some of the anti-bonding molecular orbitals that exist here that are empty can overlap with some of the bonding molecular orbitals. So if an empty orbital overlaps with a full orbital, wherever those orbitals are in space, if I have a full orbital on one carbon, and then on a neighboring carbon there's an empty orbital, and they're close enough to overlap a little bit, that actually is a stabilizing situation. Because anytime orbitals overlap, even if they're molecular orbitals, they can do constructive and destructive interference, and if there's exactly two electrons in that area of overlap, because one orbital is full and the other is empty, then those two electrons can go into the new bonding molecular orbital that's created by that overlap, and that allows them to be spread out more or delocalized a little bit over more atoms. So that's the best explanation I can give for how this structure is more stable than the other two. We know it's more stable though, because when we burn it, it releases less energy, which means it has to start at a lower potential energy than the other molecules. Also wanted to mention, in some of your quiz answers, I noticed that some of you talked about intermolecular forces. And that is a reasonable thing to consider, but if you recall, the straight chain molecules being longer and having more surface area than the more compact branch structures, they actually are more stabilized by their intermolecular forces. So if you're thinking of intermolecular forces, we know the straight chain molecule has a higher boiling point, which means the ability for this molecule to attract to neighboring molecules that are identical to it due to its surface area and ability to create small partial charges through dispersion and instantaneous dipoles along the surface of the molecule is better because there's more surface area. So these molecules are actually stabilized by their intermolecular attractions a little bit more than these molecules over here. So despite the steric hindrance between the full orbitals and slightly lower ability to form intermolecular attractions, making this molecule look like it's less stable than the other one, there's some extra orbital overlap that occurs between full and empty orbitals that actually stabilizes it more than that and makes it more stable overall, which we know because of the smaller amount of heat it releases upon combustion. So hopefully that clarifies some things and answers what's happening here with the first part of the Day 9 quiz questions. Right, so we know that if something has a high potential energy due to being unstable, it has the potential to release more upon combustion. Right, so If something's unstable, it's got the potential for change. And if that change releases energy, it's got the potential to release more energy than another structure that might not be so unstable and high in potential energy to begin with. So if you're comparing molecules' heats of combustions, the one with the greater heat of combustion should be less stable. And that's what we're looking for that quiz question. Of course, the comparison is only fair if they have the same number of carbons, right? So if I'm comparing C8H18 versus C4H10, it's not really a fair comparison. Right? If I have the ability to produce 8 moles of CO2 and 9 moles of water upon this reacting with oxygen, whereas this one would only produce 4 moles of CO2 and 5 moles of water. Well, if I'm taking the electrons and producing more of the stable substance, I'm going to release more energy, right? So we have to look at it per mole. Maybe if we looked at it per mole of CO2 produced, then we could make a fair comparison. But we can't just look at the total amount of energy released per mole of reactant if the reactants don't produce the same amounts of the products that are produced. But in this slide over here, since each one of these reactions would produce the same exact set of products, we could make a fair comparison using their heats of combustion to describe their stabilities. Alright, so then there are a few kind of just informational slides here talking about hydrocarbons, where they come from, what are their uses. The vast majority of hydrocarbons that exist come from petroleum. So any molecule that we're using in the lab that is a hydrocarbon was probably once in the ground in some form or another, was extracted. And with our society built on fossil fuel consumption, the vast majority of what's mined and produced is just simply burned to create heat or energy to fuel your car, etc. And that's obviously hugely wasteful. Not only does it produce emissions in the atmosphere that are problematic, it's also hugely wasteful because we could be taking these molecules and converting them into other important chemicals like pharmaceuticals or other fine chemicals and polymers and other materials that have a long-lasting value. So that's, I mean, even if you don't put any stock in climate change, which you should because there's a ton of evidence for it, conserving petroleum for more important uses than just burning it is something that you should consider as a noble goal. So when petroleum is mined out of the earth, it has alkanes of all different lengths, and we need to separate them because the shorter alkanes with fewer carbons have different uses than the longer ones, and so distillation is one of the first steps in that process. How does that work? Well, we know if a chain has only 5 carbons versus one that has 12, 4, 6, 8, 10, 12, well then their much lower surface area means it's not going to be able to attract to that many neighbors. With the longer molecule and with a larger surface area, it's going to be able to be surrounded by a larger number of neighboring molecules. So the London forces in the larger surface area structures are stronger overall, holding those molecules close together, making it harder for them to separate their intermolecular forces. So this is going to have a lower boiling point. We can do fractional distillation to get a better separation, where if some of the higher boiling point molecules do start to evaporate, this is exactly what we did in lab 2. If they do start to evaporate, they'll hit the copper ribbon that we use, or glass beads that are sometimes used, and the molecule can reform some intermolecular forces and drip back down as a liquid, and that should selectively distill off the lower boiling point substance first with the shorter carbon chain. So we can separate longer carbon chains from crude petroleum from the longer chains by doing distillation to some degree. So here's just a breakdown of some of the uses for the carbons depending on how many chains there are. Some of these Shorter chains are used as solvents or as precursors for chemical reactions. The ones in this range are typically used for gasoline. Unfortunately, other fuels, longer chains are needed for other types of fuels. Definitely longer chains that don't evaporate as readily are great for lubricants because they won't evaporate away, right? You put oil in your car, you don't want it to just evaporate. It needs to stay in there and keep the lubrication going. So you have to have enough carbons where it's not going to be volatile at room temperature. When you put even more carbons in there, you're talking about waxes and other polymers that have such strong London forces, they won't really even slide past one another very well. And so those are more like solids than liquids. So the gasoline fraction only makes up about 20% of petroleum. But since that has a lot of value, obviously it can be sold at a decent price. Recently that's not so much the case, but the gas prices are still probably higher than they should be. So they want to try to convert more of the petroleum they mine into gasoline than just 19%. So another thing that's done is called cracking, where under massive pressure, hydrogen is used at a really high temperature to get these molecules to collide with a strong enough force. This high pressure means the collisions are going to be strong. There's going to be lots of them happening per second. The high temperature means these things are flying around really fast. The hydrogen is going to be colliding with the structure very strongly. And if the collision occurs with enough strength, some of these bonds can break. So breaking the sigma bonds would normally create a situation where I don't have enough electrons to complete both of these carbons noble gas configurations. So that's where the hydrogen comes in. So the hydrogen can bring in one electron and form a bond here with one of the electrons from this bond that broke, and likewise here as well. So I can form two new CH bonds on the ends of these to replace where there used to be a carbon-carbon bond. And that's done a lot to the slightly longer chains to make them short enough to be used in gasoline. And that means that about almost 50% of the crude petroleum that's taken out of Earth can actually be used for gasoline and gasoline products. We talked about this a little bit. So these shorter chain carbons, as we said, they're used for gases like propane, grills and stuff like that. Gasoline, oils, lubricants, so mineral oil is used as a lubricant in a lot of situations. Tar and wax, obviously used for roads and sealants, right? If you've got like a wooden deck, you don't want water to soak into the wood because it can bring bacteria into the wood, and your wood is actually pretty polar. So you would seal that with a layer of something that's non-polar, some compound that attracts nicely to the wood that would have long carbon chains, so it would be non-polar. And then when the water comes in, it would just kind of bead up on there because the polar water molecules attract to one another better than they would attract to these non-polar sealant molecules, and that very thin layer of sealant protects the wood from moisture getting in there and bringing in bacteria, which would start to eat away at the cellulose of the wood. And the longest chain hydrocarbons, which we know as polymers, have very useful properties. These are used in plastic bags and all kinds of other plastics, and they can be converted into a variety of different plastics and materials that have a lot of different purposes. And there's a huge amount of variety there. They're usually solids. They're often flexible depending on how the chains are constructed, how long the chains are, how strongly they attract to one another. The properties can be fine-tuned. They can be pretty well controlled. If I've got this super long chain of carbons, obviously be much longer than this, it would just continue in both directions. If that long chain starts to get wound up around other long chains, and maybe there's 50 to 100 other chains directly touching its surface area, the London forces can really start to build up and hold those chains strongly together. Or if I attach other atoms here, some other group of atoms, that might block the other chains from attracting to it, or it might attract even stronger, and so I can fine-tune the strength of this material or the flexibility of it depending on the structure of the chain, how the chain is constructed and what groups are attached to it. If I want a chain that's biodegradable, I can put a linkage in here that can break. This CO bond here is can be broken with water over time, so my polymer can break down over time instead of building up in huge quantities in landfills with these really long molecules that are difficult for anything in nature to break apart, right? So there's a huge amount of variety there, and if you're ever interested in that, I encourage you to take a polymer chemistry course at some point. You'll be introduced to a lot of really fascinating molecules that have really interesting properties that are well controlled by the synthesis of the chains. Alright, so we want to get back to some of our small molecules. That was just a little bit of an introduction into some of the uses for hydrocarbons, but we want to try to build up our understanding of how these molecules behave. And so we're going to start to look again at some of the smaller molecules and their energies and how they look in 3 dimensions. So we know that single bonds can rotate. Right? So if I've got this structure here, this carbon-carbon is a simple hydrocarbon with only 2 total carbons. The carbon-carbon sigma bond can rotate, right? It involves a head-on overlap of these 2 sp3 hybridized atomic orbitals. And if I simply maybe hold one of these CH3 groups still and take the other one and rotate it by moving these hydrogens around in space, clockwise or counterclockwise, that rotation does not interfere with the overlap of the sigma bond, or the sp3 orbitals overlapping there. So there's really not much resistance for that rotation to occur. You want to be aware of the way these things look 3-dimensionally, but you also want to be aware of some of the terminology. So if I take a carbon-carbon bond and I rotate it, if the structure looks a little bit differently after rotating, it's not really a different molecule, right? I'm not going to give it a different IUPAC name, or its structure isn't really different in terms of its identity, but it is a different rotational stick for the structure, and so those are called rotational conformations or rotational conformers, right? So when we're looking at the Newman projection of this, we can illustrate different rotational conformers. So if I take this structure here, that's where the carbons are in the plane of the screen, and I rotate it to its side a little bit, so this carbon with the red hydrogens comes slightly out of the screen, and the carbon with the blue hydrogens goes slightly behind the screen. Here are this carbon's like a little bit in front of the other one. Still the same molecule. If I rotate it a little bit more until this front carbon lines up directly in front of the back carbon, that's when I get the Newman projection. So this is carbon 1, this is carbon 2. The point here in the middle is meant to be carbon 1. If I rotate this so it's directly in front of carbon 2, I wouldn't be able to see it. So to represent carbon 2, that's what the circle is there for. Right? So if I have this particular rotational conformation of ethane, the hydrogens are all staggered around. They're not eclipsing or lined up on top of one another. They're all spread out. Right? If I take this front carbon, though, or the carbon-carbon bond between those carbons, and rotate it 60 degrees, oops, ignore that right there. The front carbon, if I hold the back carbon still and just rotate the front carbon 60 degrees, then all these hydrogens would be lined up. And that would look something like this. So my front carbon's hydrogens would just be rotated 60 degrees. My back carbon's hydrogens would be behind those. You wouldn't be able to see them. But we want to at least show where they are, so we just kind of show that they're pointing in the same direction as the other ones, straight back. So the relationship between these two structures is that they are rotational conformers. They're only different in the rotation of one of the single bonds. They are both named ethane. They are not different from one another ultimately. Does anyone have any questions about that? So I created a few videos where I use a handheld molecular model to help explain this stuff. So after lecture, I encourage you to watch those videos. Hopefully that will really help to cement what we're talking about. So typically when we draw an organic chemistry structure, we put the carbons in the same plane as the screen. But when we draw a Newman projection, sometimes there are certain concepts that are easier to see if we take one of the carbons and bring it out in front of the screen so it's eclipsing the other carbon behind it, which is what the circle is meant to represent. One of the things that's easier to see when we draw a Newman projection is the torsional angle, or whether or not one hydrogen on one carbon, or it doesn't have to be hydrogen, it could be any group, is aligned with the hydrogen or group on a neighboring carbon. Right, so if I draw that carbon-carbon bond like this, and I have my front hydrogen and back hydrogen in the same plane, they're both in the plane of the screen, and then I've got another hydrogen here pointing out at me and one pointing away, and then over here one pointing out at me and one pointing away. This is where they're eclipsing. Alternatively, if I draw this other hydrogen down and then show the other hydrogens in their tetrahedral positioning, here the hydrogens are staggered. Right, so look at this. This hydrogen is in the plane of the screen, right, because it has a regular line. It doesn't have a dashed or a solid wedge here. On the neighboring carbon, this hydrogen's lining up with the space in between these hydrogens, right? Because this one's coming out at me a little bit, and this one's pulling away. This hydrogen is right in between there. It's really hard to see when I draw it that way. It's much easier to see that in the Newman projection. All right, so if I'm looking down this angle with my eyeball, the front carbon, the front hydrogen's pointing straight up, and that's exactly what I see right here. On the front carbon, I've got one hydrogen pointing a little bit down out at me. So if I'm imagining my eye right in the plane and I'm looking here, then this hydrogen would be on my right hand side. So this we'll just call A and B. This would be A and this would be B. On the back carbon, I've got one hydrogen pointing straight down in the same plane that this hydrogen is pointing straight up. And that's exactly what I see. Those are called anti with respect to one another. Anti means that I have 180 degrees rotation between a group on one carbon and the group that's directly behind it on the neighboring carbon. The other hydrogens on that back carbon ones, if my eye is in the plane and I'm looking down at this angle, one of those hydrogens is pointing out of the screen, so that would be on my right. We'll call that one C and this one D, so this would be hydrogen C. And hydrogen D would be pointing away from you if you're looking toward the screen, but if you're in the screen, it would be on your left. So hopefully you can see how this structure translates into a Newman projection, and how the advantage of the Newman projection is you can see all these hydrogens on the front carbon, the ones in red, are staggered or spread out from the hydrogens in blue on the back carbon. If the front carbon gets rotated, or actually if I rotate the back carbon in this case, so that two hydrogens are in the same plane, these are both in the plane of the screen. Now the two solid wedge ones are in the same plane eclipsing, and the two dash ones are in the same plane eclipsing. So if I drew a Newman projection for that, the front carbon would still have a hydrogen pointing straight up, and it would have a hydrogen pointing down to my right and down to my left. Right, this would be A and B. If I'm in the screen looking in this direction, the one that's coming out of the screen would be on my right. The back carbon I would show with the circle. Otherwise, it would just be behind the front carbon and I wouldn't be able to see it. So we're just putting that to remind ourselves that it's there directly behind the front carbon. If I'm looking down that angle, it's directly behind it. So this hydrogen would be pointing straight up, and so that would be back there, coming off the back carbon, right behind the other hydrogen. They're eclipsing one another. We'll call this one A and this one B, and then there's a hydrogen coming out of the screen, so if I'm in the screen, it's going to be on my right, coming off the back carbon, right? So notice this line here, this line here doesn't go all the way in to the center. It starts on the circle because that hydrogen is on the back carbon, and that circle represents the back carbon. And then there'd be the other hydrogen B on the back carbon, eclipsed by the hydrogen B on the front carbon. So if I'm looking at these two structures, the standard bond line representation of ethane, it's really hard for me to see that there's no eclipsing here, but there is eclipsing here. And that eclipsing makes this unstable to an extent. Because this is a full cloud of electrons and another full cloud of electrons. They're pointing slightly away from one another, but their clouds are big enough to cause proximity between the two electrons in this molecular orbital and the two in this molecular orbital, and that causes some repulsion. And that makes it unstable or higher in energy. It's hard to see that in the bond line structure, but I can see it much better in the Newman projection. I can see this hydrogen and this hydrogen are right aligned with one another, and I can see how close their bonds look, and that helps to remind me how unstable it is when things are eclipsing. And when I have eclipsing groups repelling one another, that's called torsional strain. Torsional. Torsional strain. There's no torsional strain if everything is staggered. In this structure here, everything's all spread out all the way around. There's no torsional strain. In this structure here, there's torsional strain because of eclipsing. Torsional strain is just for groups eclipsing on adjacent atoms. They can't be farther away and then being on adjacent atoms, otherwise it would be a different type of steric hindrance. So let's practice this one. So there's also a video that explains this example if you want to check that out. So here again, we're looking down this angle, so I want to number these carbons. Got more than just two carbons here, but I'm looking down the carbon 2, carbon 3 axis. So carbon 2 is closer to my eyeball than carbon 3. So carbon 2 is the front carbon, and carbon 3 is directly behind it. What's bonded to carbon 2? Well, it's not shown, but there's a couple hydrogens here. If I want to put those in my Newman projection, I can. If you leave hydrogens out of your Newman projection, that's fine, unless the question specifically asks you to draw them. But on carbon 2, if I'm looking down from this angle where the eyeball is, this methyl group, which is what carbon 1 is kind of pointing down from that. So carbon 1 is coming down from carbon 2. On the front carbon, I've got two hydrogens. If I want to draw those here, I can. I don't have to. Right? One is kind of coming up to the right and up to the left if I put myself in the plane of the screen. The back carbon 3 has a chlorine in the plane that my eyeball's in, pointing up. So that back carbon would have a chlorine pointing up. Right? Notice the chlorine is pointing out up at an angle that's directly opposite in direction from where carbon 1 is. So in my Newman projection, chlorine is pointing the opposite direction from where carbon 1 is. So now the tricky part is, where is carbon 4? I really have to make a model to look at the model, or I have to be really good at thinking of this thing three-dimensionally and imagining myself in the plane of the screen looking down in this direction. Some people are just naturally better at that than others. So there's no shame in getting the model and checking yourself, especially since you're allowed to use models during the exam. But if I'm looking down at this angle, this dashed wedge indicates that this methyl group, or carbon 4, is back behind the plane of the screen. So if I'm in the plane of the screen looking in this direction, this methyl group is on my left. And so I have to draw it here on the left. That's carbon 4, and there's not shown, but there'd be a hydrogen which I could put in here if I wanted. And if I want, so that would be the Newman projection for this molecule as it's drawn, looking down the carbon 2, carbon 3 axis. So what if I looked up the other direction? So what if my eyeball were here, looking in the other direction? Well, then carbon 3 would be the front carbon. And the back carbon would be carbon 2. On the front carbon, the chlorine's sticking straight up. If I'm in the plane and this hydrogen's pointing out of the plane, that's going to be on my left. And the methyl group would then be on my right. Right, this hydrogen, the chlorine, and the methyl group are all on carbon 3, so their bonds all extend all the way to the interior, which is the point in the middle, which is what represents carbon 3. Carbon 2 behind has 2 hydrogens sticking up and to the sides. And it has another carbon, which is carbon 1, pointing kind of straight down from that. Oops. 1, 4. So these two don't look the same. Obviously, the way I draw my Newman projection is going to depend on the angle with which I view the molecule. It will also depend on the way this molecule is rotated around the single bonds. And since we know the single bonds can rotate freely, there's a lot of different ways I could represent this molecule with the Newman projection. Here are just 2 ways that represent the current rotational state of this structure. If I were to rotate it, maybe so that this chlorine rotated down, obviously the Newman projection would look different. So we want to get some more practice looking at those types of situations. But before we do, we want to talk about the energy or stability of the molecules in different rotational states. So, as we said, torsional strain has to do with repulsion between groups on adjacent atoms. So this carbon is bonded to the one directly behind it. A hydrogen on one carbon could create torsional strain with a hydrogen on another carbon, but they won't create torsional strain unless they are eclipsing. So if I have a staggered Newman projection where all the atoms are spread out, I have this torsional angle between these 2 hydrogens, or also called dihedral angle, of 60 degrees. So what does the angle have to be for there actually to be torsional strain or repulsion between these hydrogens on adjacent carbons? Well, the angle between groups on adjacent carbons has to be 0 degrees. So the torsional angle has to be 0 degrees to create an eclipsed structure to create torsional strain, which is the repulsion created by those groups if they eclipse one another. So we can always talk about the dihedral angle. We should also talk about the angle that looks like the hydrogen on the same carbon have. Right, so this hydrogen here and this one here on the same carbon. Geometrically, the angle here looks like it's about 120. What should it really be? For hydrogens on the same carbon, if the carbon is sp3 because it has 4 single bonds, the angle here should be 109. So that's pretty close to 120, right? And when we're drawing our zigzags, we're not too concerned with the exact angle here when we draw it. We're not going to get a protractor and make sure it's 109. 109, 120 are pretty close, so either way is reasonable. So that's basically what you would expect to see there. And these 3 atoms are spread out. they're not flat in the plane, right? So you got to remember, even if this carbon has a carbon directly behind it, so it makes 4 bonds plus 3 bonds to 3 hydrogens, these 3 CH bonds are not all in the same plane. They would all be slightly coming out at you, and if you make a model, you'll see that they're all kind of coming out at you, so the angles are a little bit less than 120. So you got to remember that. In a Newman projection, the angles for hydrogens on the same carbon are 120, even though in reality they're actually 109, because all 3 hydrogens are slightly coming out of the screen at you just a bit. So then, what's the dihedral angle between this hydrogen and this one? Right? Dihedral angle is for groups on adjacent carbons. Right? This hydrogen's on the front carbon, this hydrogen is on the back carbon. Obviously, they're 180 degrees. So that's a 180 degree dihedral angle, 60 degree dihedral angle between atoms on adjacent carbons if they're just staggered a little bit. So as we said, if we hold, in this case, if we hold the back carbon still and we rotate the front carbon, if we rotate the front carbon 60 degrees, all these hydrogens on the front carbon will line up with the hydrogens on the back carbon, and that's how we go from a staggered to an eclipsed conformation. In the staggered conformation, the dihedral angles are all 60 degrees, there's no eclipsing, there's no torsional strain because this electron cloud is as far away from the hydrogen's electron cloud as it can get. If it gets any farther away, then this hydrogen will get too close to the other one. Right? So staggering everything directly in between is the most stable way to have groups on adjacent carbons positioned or rotated. If you eclipse them, that's the least stable or highest in energy, because now the electron cloud of the hydrogen and this hydrogen are closer together. They're not really overlapping, right? If we show the carbons in a different angle, this hydrogen's bond and this one, they're kind of pointing away, but they're full of electrons, not lone pairs, but they're full of electrons being shared with these hydrogens, or it could be other groups attached there. The bigger the group, the bigger the electron cloud, there's going to be a little bit of repulsion in between those electron clouds. And we can measure how much that makes the molecule less stable if we want. And so that's been done, and the difference is about 12 kilojoules per mole. Not a very large amount. Every time we rotate 60 degrees and they eclipse, it goes up by 12 kilojoules per mole in potential energy. Every time we rotate it so they're staggered, it goes back down. So all the eclipsed are equivalent energy, and all the staggered are equivalent in energy, and they're all more stable because there's less repulsion between groups on adjacent carbons, versus if they're eclipsed, then the repulsion is maximized between groups on adjacent carbons. And when I have groups on adjacent carbons eclipsing and repelling, that is called torsional strain. So if it's 12 kilojoules per mole in energy higher to eclipse them, in total, that means each one of those interactions adds about 4 kilojoules per mole to the instability or energy. And that's enough where when it reaches equilibrium, about 99% of the molecules will be in the more stable staggered conformation. So what that means is, if my molecule looks like this, if it rotates that front carbon to the point where it eclipses over here, as soon as that happens, it's going to rotate back out of that and either go back to where it started or over here to the next staggered conformation. So 99% of the molecules will be in one of these forms, and only 1% will be in the other form, and that will only happen for a second because it will rotate out of that due to the torsional strain between the hydrogens. If we increase the temperature, we would get more of the molecules in this state. Because what happens is, if we start with one of these staggered ones, as it starts to rotate a little bit, and its electron cloud starts to repel this electron cloud on the neighboring carbon, if it's not a very fast moving molecule and the temperature is relatively low, there isn't going to be enough kinetic energy to continue all the way until it's eclipsing. If it gets a little bit close and starts to repel, it'll just go back. It won't have enough energy to even make it up here to this higher energy point. So if I increase the temperature and my molecules have more kinetic energy, they're bouncing around more, they're colliding more, there's more motion, there's more rotation, more vibration. At a higher temperature, there's enough energy to overcome that repulsion and get the hydrogens to actually eclipse for a little while. And so I'll have more molecules in the eclipsed state at a higher temperature than if I were at a lower temperature. So there's also a molecular orbital explanation that helps explain the difference in energy, right? We said that the staggered is 12 units of energy, kilojoules per mole, more stable than the eclipsed. And the main reason for that we would invoke is to say that the full orbitals overlapping makes it unstable. But there's also another factor, and that is a full orbital overlapping with an empty orbital, and that actually makes it more stable. So this particular picture here is obviously not a Newman projection, but it shows the staggered view of this ethane molecule. Right, this hydrogen is in the plane of the screen. On the neighboring carbon, the hydrogens are staggered. One's coming out at me, one's pointing behind. There's nothing right in the plane of the screen to overlap there and create repulsion. So not only am I able to avoid torsional strain and the repulsion and instability associated with torsional strain because there's no eclipsing groups, I actually do have an eclipsing full orbital with an empty antibonding orbital. So these antibonding orbitals are empty, but when they still exist, and when they overlap with a full orbital, I've got two electrons total in my full orbital, and obviously 0 electrons in the empty orbital. So if these overlap a little bit, it can create a new molecular orbital with more constructive interference and put these electrons actually in an orbital that delocalizes them a little bit over both carbons and allows them to attract to both carbons a little bit instead of just one. And that stabilizes the electrons a little bit more. So the difference in energy between the staggered versus the eclipsed is actually two reasons. One, because the staggered avoids the torsional strain, the torsional repulsion, and that would occur when the eclipsing groups get a little bit closer together. And two, because there's an extra molecular orbital that delocalizes the electrons when the full sigma bond overlaps the empty antibonding orbital. So we'll call that's called sigma star. If you see a star next to a sigma or a pi, it's the antibonding version of that orbital. So the bonding sigma bond on one carbon can overlap with the empty antibonding carbon on antibonding orbital on the other carbon, and that orbital overlap is stabilizing. So orbital overlap is stabilizing when there are two total electrons in the area of overlap. It's destabilizing when there are more than two electrons in the area of overlap. And that is a really key point that helps to explain the energy difference here. So I want to expand on this a little bit and talk about situations where now instead of only two carbons we have three. Right, so instead of ethane, I've got propane. So if I'm looking down the same angle, actually let me draw that a little different. Let's draw it like this. So here's my propane, right? 1, 2, 3. So if I'm looking down the same angle with my eyeball, carbon 2 is in front. That's right here. It has a methyl group sticking straight up from it. So that's here. Carbon 3 is behind, and it just has 3 hydrogens on it. So if those hydrogens initially are staggered with that methyl group, because the methyl group's lined up between them instead of eclipsing with one of them, that creates the lowest energy state for propane. If I rotate the front carbon now, so this 60 degrees, so this methyl group starts to eclipse with the hydrogen, Now I've got an even more unstable situation. The methyl group's electron cloud is even bigger than a hydrogen, and it's overlapping with a hydrogen. And so now I've got more overlap between full orbitals, so it's even more unstable or even higher energy. So instead of a 12 kilojoule per mole difference, I got 14 kilojoules per mole. And if we break that down per interaction, we know that a hydrogen eclipsing a hydrogen is already, we determined that was 4 kilojoules per mole. So we have a total of 8 total kilojoules per mole for those two reactions. So if we subtract that from the total, we get 6 kilojoules per mole for that hydrogen methyl group interaction. If you had asked me, I probably would have expected it to be more, but that's what the experimental calculations show. So a methyl group's just big enough that its electron cloud with all these CH sigma bonds that are full electron orbitals start to get too close to the full electron orbital for that CH sigma bond on the back carbon, and that repulsion makes it significantly less stable. I want to expand that, talk about 4 carbons. So there's a video for this you can check out on Canvas, also on my YouTube channel. If I have 4 carbons, this could be my bond line representation. If I'm looking down this angle, here's my front carbon. There's a methyl group sticking straight up on it. There's a hydrogen pointing out at me and one pointing away. On the back carbon, that would be represented with the circle. There's a methyl group sticking straight down. And there's a couple hydrogens, one pointing out at me and the other kind of pointing away. So those will be on my right and left if I'm in the screen looking down at that angle. So here the energy is a little bit more complicated. Not all of my staggered versions are equal in energy, but all the staggered versions are definitely way lower in energy than any of the eclipsed versions. So in general, you want to remember that the torsional strain is the biggest factor that affects how molecules rotate. If they rotate in such a way where any of their groups are lined up and repelling, that's very unstable. And if they line up the biggest groups with one another on adjacent carbons, that's extra unstable, right? So the energy here, the potential energy here is higher than these other peaks by 3 kilojoules per mole because of the extra repulsion between those two methyl groups. What I have down here, everything's staggered in each one of these 4 on the bottom. The difference is when I stagger the largest groups anti to one another, or 180 degrees dihedral angle, that's a little bit more stable than if they're 60 degrees dihedral angle. So sometimes I ask students, what's the most stable to least stable dihedral angle for large groups on adjacent carbons? So let's just talk about that. Right, so I've got 2 carbons. The most stable, which would be lowest potential energy, is to have my biggest crowding groups 180 degrees apart. 180 degree dihedral angle. One group on the front carbon, one group on the back, apart from one another as much as possible. The next most stable situation is going to be a 60 degree dihedral angle. So one group here, and the other group on the other carbon coming off a 60 degree dihedral angle. The next least stable, the next most stable, or working toward the less stable molecules, is where the atom on the front carbon and the atom on the back carbon are 120 degrees dihedral angle. And that difference is what's most confusing when we talk about this. You're thinking, well, if the 2 largest groups are 120 degrees, wouldn't that be farther apart than 60 degrees? Shouldn't that be more stable? But no, it's less stable. And the reason for that is because there are other groups at play. There's another group here that it would be eclipsing with. So 120 degree dihedral angle creates eclipsing between all the atoms all the way around, and that always is going to be less stable than staggering. So if I can put my large group staggered between other groups, that's always going to be more stable. And so don't forget those hydrogens are there. 180 degrees staggered is better than 60 degrees staggered, but staggered is always better than eclipsed. And so then the worst situation would be if those two groups were actually eclipsing one another. If I put my two least stable groups at a 0 degree dihedral angle, that's going to be really unstable because of the biggest full electron clouds repelling, making it very unstable. So hopefully that helps with that concept. And so here we're learning a couple new terms related to that. So all three of these structures are staggered. We said the anti is when my largest groups are 180 degree dihedral angle. There's a special term for groups that are staggered but at only 60 degree dihedral angle, and that term is gauche. Gauche interactions cause some repulsion, and that's why we saw the gauche 60 degree dihedral angle between my largest electron groups slightly higher in energy than the anti that were on either end there. And so we can see it's about a 4 kilojoule per mole difference, specifically when the groups are methyl groups, between the gauche and the anti. If the groups are even larger, there'd be a larger energy difference between those two states. So how much does an eclipsing methyl group eclipsing another methyl group affect the stability? Right, so let's go back here. We said there's a 19 kilojoule difference between the full anti-staggered version and the most unstable eclipse version. That's 19 kilojoules per energy difference there. So if we know the full repulsion between these two groups, combined with the repulsion between those, creates 19 kilojoules per mole more energy than if the methyl groups were staggered, and thus the hydrogens will also be staggered. If we rotate this around, we know the hydrogen eclipsing a hydrogen is 4 kilojoules per mole each. So if we subtract that total, 4 each, gives me a total of 8 kilojoules per mole more unstable for these eclipsing interactions. If I subtract that from 19, I get 11 kilojoules per mole just for the methyl-methyl interaction. And the larger these groups are, the more unstable it makes it. So methyl groups are bigger than hydrogens. Almost 3 times more unstable for 2 methyl groups to eclipse than for 2 hydrogens to eclipse. If I put ethyl groups here, it'd be even more unstable. So if I'm asking you ever for the least stable rotational conformation for a structure, it's always going to be where the biggest groups eclipse with one another. And then this table just summarizes the interactions we just talked about. You definitely don't have to memorize these numbers, but you should know relative to one another how much instability it introduces, right? So the smaller groups eclipsing makes it a little less stable. Make one of those groups a little bit larger, makes it a little bit more unstable. Make both groups larger, the larger I make them, the more unstable it makes it. If I bring large groups into a staggered position, it's not going to be as unstable as if they're eclipsing, but it's still going to be a little bit more unstable than it would be if they were anti. And so that's going to be, there's no extra energy associated with that. That'll just be 0, because that's the lowest energy state for a structure. It is to have the largest electron clouds attached to my adjacent carbons completely apart in a 180 degree dihedral angle, which is called anti. Alright, so let's look at this example here, and we'll talk about the second quiz question. So here I want to draw a Newman projection, so I might ask you to draw one, or I might draw one and ask you to interpret it into a line structure like there was in the quiz question. So if I need to draw a Newman projection, if I give you a name, so this question requires you to have 2 different skills developed. The ability to interpret names and the ability to draw a Newman projection from a bond line structure. So I would first draw the bond line structure for this name. To start from the Newman projection directly from the name would be unreasonable. So I know I've got 6 carbons in my main parent name. Hex means 6, so I would just draw 6 carbons. And spreading them out makes it as stable as it can be. So if I want to start with the lowest energy conformation, I want to spread out my zigzag. I don't want to do this because this is going to create a lot of eclipsing, right? If I'm looking at these 2 carbons, these groups are right next to one another. So that might help me to draw the highest energy conformation, but I usually want to start with the lowest energy conformation, spread out my zigzag structure as much as possible. And so what else is on here other than my 6 carbons in my parent chain, which I should just number to keep track of. Make sure I have the correct numbers. Hex means 6. I've got 2, 2, 3, 5, 5 pentamethyl. So this part here is telling me I have 5 methyl groups, and it's telling me which carbons those methyl groups are on. Meth means 1 carbon, so I've got 1 carbon substituent on carbon 2, 2, 3, 5, and 5. So really this name is incomplete in one way. So let's just take a look at this. The methyl groups on carbon 2, then since there are 2 identical ones here, I know it doesn't really matter which one I show pointing out at me or pointing away, but any carbon that has 4 bonds, only 2 of those bonds can be in the same plane. So my parent chain, I put all in the same plane as the screen. That means my 2 methyl groups, one has to be pointing out at me and one has to be pointing away. And I can say the same thing about the methyl groups on carbon 5. Doesn't matter which one I show with the solid wedge and which with the dash, but one is solid and one is dash. When it comes to carbon 3, though, I've got a situation. The name does not clarify whether the methyl group on carbon 3 is sticking out at me or whether it's pointing away, and it actually does make a difference. So this is a topic that we're going to get into in chapter 5, and that has to do with the spatial positioning of groups on a carbon chain. Sometimes it makes a difference, sometimes it doesn't. If I make this methyl group here with a solid wedge, it's not the same structure as if I make it with a dash wedge. Those 2 structures would not be superimposable, they're not identical, and they have to have different names, and so we're going to talk about that in chapter 5. But for now, let's just assume it had a solid wedge so we can answer this question. So the question tells us to view the projection down the carbon 3, carbon 4 axis. So I numbered my parent chain. This is carbon 3, this is carbon 4. So my front carbon, I'm viewing it down the 3, 4 axis. This is my front carbon, this is my back carbon. So when I draw the Newman projection for my most stable version of this structure, carbon 3 is my point in the middle. Carbon 4 is directly behind that. I'm going to draw that over here, and hopefully you won't have any interference. Carbon 4 is directly behind it. So what's on carbon 3? Well, sticking up from that, I've got, right, if I'm in the plane looking down the 3, 4 axis, and my eye's looking in this direction, I got to imagine myself there in the screen. This carbon 2 is coming straight up from carbon 3, and it's got 3 more carbons attached to it. So this is 2, and this is 1, and those are my 2 methyl groups that are on carbon 2. What else is on 3? The methyl group with the solid wedge. That means it's coming out of the screen. So if I'm in the screen, it's going to be on my right-hand side. There's also a hydrogen there. I can leave that out if I want, or I could put it in. Carbon 4 is the back carbon. That's the circle. Obviously ignore this. That's a bug in PowerPoint. Carbon 4, if I'm looking down from this direction, this carbon 4, carbon 5 bond should be pointing straight down. And then carbon 5 has 6 and 2 methyl groups. Carbon 4 also has a couple hydrogens that aren't shown. So I could put those in here if I want. So that's definitely the most stable version of this structure, because this very large group and this very large group are anti with respect to one another. So I could draw the bond line structure for the highest energy or least stable version of this, or I could just take my Newman projection and rotate it. I can hold the back carbon still, meaning that I'm going to keep the things attached to it positioned in space the same way they were. But if I want to make it the highest energy it can be, just to represent what that would look like, I want to eclipse the two biggest groups. So I'm going to have to rotate this front carbon a full 180 degrees so that this terp-butyl group is eclipsing the other terp-butyl group. So that means every one of these groups on the front carbon is going to rotate 180 degrees away from it where it was. So the terp-butyl group will be pointing off the front carbon straight down. And those two would be creating a huge amount of torsional strain, a huge amount of repulsion between eclipsing groups on adjacent atoms. This methyl group would end up here, and the hydrogen would end up there. So I've got a hydrogen-hydrogen eclipsing. We said that's not very much, 4 kilojoules per mole. A methyl hydrogen eclipsing, 6 kilojoules per mole. A terp-butyl eclipsing with a terp-butyl is huge. That'll be a lot of kilojoules per mole. I don't know offhand, probably somewhere around 20 or so kilojoules per mole, because those are massively crowded groups with huge electron clouds that would cause a huge amount of repulsion. So definitely practice more like that from the textbook. And so here was the quiz question. I was really impressed with most of your answers, even the early ones. I didn't really have to correct too much on this. Y'all did a great job of, for the most part, of converting this into a bond line structure and naming it. So I tried to make the structure look like the Starship Enterprise just for fun. So this front carbon here, it's bonded to the back carbon. So I can start with that. So this front carbon is bonded to the back carbon. They'd be eclipsing. The front carbon has a methyl group, and it's also part of this 5-membered ring. Alright, so if I'm looking down this angle, I've got the ring and the methyl group coming off the front carbon. The back carbon, which I drew a little circle here for since that's the circle behind, it has a hydrogen bonded to it, and it has an ethyl group and another ethyl group. Right? So you got to remember, if a line extends all the way in to the center of a ring, it's not indicating that that group is on the back carbon. It's indicating that group is on the front carbon. So the back carbon has only things that are drawn to the circle. So there's a hydrogen, an ethyl group, and an ethyl group. And notice the hydrogen is staggered in between those two parts of the ring. So this would be my hydrogen, my ethyl group, and my other ethyl group. So there's my bond line representation. I want to name this structure. So there's actually a couple different ways you could name this. If you think of the ring as being your longest parent chain, it would be cyclopentane. You could also have thought of this 5-membered grouping of carbons here, 1, 2, 3, 4, 5. That could just be pentane, and then you could just name the rest as a substituent. Either way is acceptable. So since the ring and the other chain have the same number of carbons, you can name either as the parent as far as I'm concerned. In that situation, I think probably the ring actually is a priority, but that's a level of nuance for the naming system I don't expect you to worry about. So if I make the cyclohexane my parent, what does my parent have? Well, on carbon 1, this is definitely carbon 1, right? I wouldn't start numbering somewhere else. I want to start numbering on the carbon that gives the groups the lowest numbers. So on carbon 1, I've got a methyl. And then I've also got to name this thing. So this thing has 1, 2, 3 carbons in the longest chain of consecutive carbons that I can make. So it's a propyl. but that propyl has on it a 2-carbon chain that's connected to carbon 1 of the propyl. So I've got an ethyl on my propyl, and it's on the first carbon of the propyl. So it's a 1-ethyl propyl. So on carbon 1 of my parent chain, I've got a methyl, and on carbon 1 of my parent chain, I've got a 1-ethyl propyl. And so alphabetically, this would come first. So I would do 1-ethyl propyl, 1-methyl cyclohexane. These parentheses are absolutely necessary. The ethyl is not on carbon 1 of the parent. The ethyl is on carbon 1 of the propyl. And that's what the parentheses are making clear.
Isn't it cyclohexane?
Oh, yeah. Yes. Sorry. Yeah, obviously, pent is 5, hex is 6. Absolutely. Yeah, you got to get your prefixes straight there. Sorry about that. Alright, so then we want to draw the highest energy conformation for this Newman projection. So if I already have a Newman projection, all I have to do is rotate it so that the largest groups are eclipsing. So on the front carbon, I've got a methyl, and then I've got this ring. And there's more carbons and hydrogens in the ring, so that makes it a larger group. On the back carbon, I've got these ethyl groups that are clearly larger than the hydrogen. So here I need to rotate this 180 degrees to get the largest groups to eclipse if I want it to be the highest energy or least stable structure. So for me, I don't know why, I just find it more intuitively easy to do this if I keep the carbon still. So I'm going to put the groups on the back carbon. Oh well, that's fine, I'll leave it there. I'm going to put the groups on the back carbon right where they already were. And I'm going to rotate the front carbon. I've got to rotate it 180 degrees to get these two parts of the ring to eclipse with the ethyl groups where it'll be least stable. So from the front carbon, I've got my methyl group 180 degrees away from where it was, and my five-membered ring eclipsing with the ethyl groups. That's a little bit sloppy there. Any questions or other corrections on that? Alright, so that gives you a pretty solid basis for Newman projections on molecules that are made of chains. And you should definitely practice those up. You look at some of the textbook practice problems before next week, when we're going to have an exam on this starting next Tuesday. We want to look at some ring structures now, and we're going to look at the stability of rings and talk about the factors that are relevant there. So cycloalkanes have my carbons connected in a ring. Obviously, if it's an alkane, it still doesn't have any double or triple bonds. And we want to consider, what would these rings look like if they were flat? Some of them are flat. Most of them are not. And I made some videos with a handheld model so you can see the three-dimensionality of these structures with the model, which is better than just what's on the PowerPoint slide. So I encourage you to watch those videos as well if you get a chance sometime soon. So if I just look at the geometrical shapes, if I have 3 carbons or 4 carbons or 5 carbons, I have a triangle, a square, pentagon, hexagon, etc. If I look at the angles here, most of these angles are not close to what they should be. Here the pentagon is the closest you can get. 108 is pretty close to 109.5. So this distance between this electron cloud and this electron cloud is far enough apart to avoid significant repulsion between those electron groups, which is good. So when I have rings with fewer than 5 carbons, the situation is the electron cloud here for one of these sigma bonds and the other sigma bond, they really start to overlap, and that creates a lot of repulsion. And so this three-membered ring is really unstable. Even the four-membered ring, though, the cloud for one sigma bond and the other sigma bond are much closer than would be preferred, and so that creates a lot of repulsion. If you look at the larger rings, you might say, well, this is even better. If the angle is larger than 109, then the cloud for this sigma bond and this sigma bond are even farther apart than they would normally be, and that should avoid some of the repulsion they would have if they're at 109 degrees or 108. But the problem with that is there are also hydrogens attached here. So if I have a hydrogen here and here, if there's only so much three-dimensional space around this carbon, and if it's a sp3 hybridized carbon and it's tetrahedral, the optimal angles are 109.5, because if I stretch any of the angles to a degree larger than 109.5, like 129, it's only going to push those closer to the other bonds that are present around that carbon. Right, so the reason 109.5 is the optimal bond angle is because that spreads everything out as much as possible. And if I spread anything larger than 109, it's forcing it closer to something else, which causes a specific repulsion there between those electron clouds. So really, the five-membered ring is looking pretty stable. But what we're going to see here as we go through is the angles can change if I don't make the structure flat. Right? So in math class, if you took geometry, you learned that 120-degree angle is what we expect in a six-membered ring. But that's if it's flat. And so we're going to see some of these are not going to be flat in their most stable conformation, and we want to be able to explain that in detail, which is what we're going to talk about now. So first of all, we can measure the energy associated with these rings, and so we can use heats of combustion like we talked about at the beginning of today. Heat of combustion tells me how much energy is released. More energy released upon combustion means it was more unstable to begin with. But if you recall, what we said was it's not really a fair comparison if they don't have the same number of carbons. So three-membered ring versus four versus five, etc. That's not a fair comparison. So to make it a fair comparison, we want to report it per CO2 group, per CO2 molecule produced, or per CH2 group reacted. Right? So if one reaction produces 3 molecules of CO2 and the other produces 5 molecules of CO2, well, CO2 is relatively stable, so the more that it produced, the lower in energy it's going to be, the more energy is going to be released. It's going to make it seem like it started much higher in energy to begin with if it's releasing all this energy. So we have to divide that value by the number of carbons so we can really make a fair comparison between all of those. And so that's what this value here is. It's the amount of heat released upon combustion divided by, or per, the number of carbons in the molecule. That gives us a fair comparison. Now we can look at these numbers and say if the number is larger, it started at a higher potential energy to begin with. And so it was less stable. And so we want to look at these structures and try to understand why the three-membered ring is the least stable, why the four-membered ring is still relatively unstable, why the five and six-membered ring are relatively stable, especially the six-membered ring. We're going to focus a lot on that because it is so stable. It's the most commonly found one in a variety of molecules. We're going to see that one a lot, so we want to understand it in a little bit more detail. And then we won't really talk about these too much, at least not today. We'll talk about those a little bit later in the semester. Alright, so let's take a look at angle strain. We were already saying in the three-membered ring, the sigma bond electron clouds are way too close together. The repulsion between them creates something called angle strain. So we're going to talk about ring strain. Ring strain is a combination of two things: angle strain and torsional strain. There are a couple of other types of strain that can factor in there, but these are the main two that we're going to focus on for the most part. So angle strain occurs when electron clouds on the same atom repel. right? I've got one atom, I've got two sigma bonds connected to the same atom. If they get too close, because the angle's too small, that causes repulsion. That's angle strain. It makes the whole structure less stable, so it will release more energy when it undergoes combustion. If the angle's too large, that pushes the groups closer to the outside hydrogens, as we said. And so it still produces angle strain. So anything that's not 109.5 is going to produce at least some angle strain, because for an sp3 hybridized carbon, any bond angle that's less than 109.5 is going to cause repulsion. And if one of the angles is greater than 109.5, it by nature forces some of the other groups closer together to cause repulsion. Angle strain is a big one. Right, if we have two electron clouds on the same carbon, they're close together. If I force them even a little bit closer, it's going to cause it to be significantly less stable. So that's why I labeled this number 1. It's the main reason why there's instability in these really small rings, because of the proximity of the electron cloud. So torsional strain, as we were talking about earlier, is when electrons repel on adjacent atoms. Right? That's when you have two different carbons, and maybe the hydrogens or other groups attached to them are in the same plane. Right? They're not on the same carbon, so they're not getting as close together. It's a minor repulsion, right? We just saw that two hydrogens eclipsing is 4 kilojoules per mole. It's not that much, but it does make it a little bit less stable. So if we could stagger these hydrogens instead of eclipsing them, it would make it a lot more stable. So we want to see how that is relevant in the context of some of these rings. So we'll start with the 3-membered ring and work our way up to 6. So the 3-membered ring, if you look at the model that I show in the video, more than the angle strain, there's also torsional strain. So let's just look at the angle strain. So we would expect normally these sigma bonds would have their orbitals pretty effectively overlapping. But if I do that to make all these sigma bonds all the way around the ring, well, there's areas where the full orbitals on the same atom start to overlap. That creates a lot of repulsion. So these sigma bonds are actually very weak, because instead of the sigma bonds facing head on like they really should, what you really end up with are these bowed out sigma bonds. They can't get any closer together, the blue areas of electron density, because they're full of electrons and they repel. So they get forced out, and that means there isn't much overlap. And so the molecular orbitals that are created don't put the electron density right between the nuclei where it would be most stable. And so that creates a really unstable ring. So because a 60-degree angle would be too much repulsion, they don't get that close, but then that creates another problem where the sigma bonds are really unstable, because the overlap that creates those sigma bonding molecular orbitals isn't very effective. So let's look at the torsional strain. Right, so if we have a 3-membered ring and we kind of try to draw a Newman projection of that, down here, what I see are these hydrogens on this carbon and nitrogens on this carbon are eclipsing. They're lined up, and that's what we see here. Right, this hydrogen on one carbon and then the hydrogen on the neighboring carbon, they're causing eclipsing. That happens all the way around the ring. That also makes it unstable. So those two things, the angles and the sigma bonds not being stable, as well as the torsional strain, are mainly what contribute to the high potential energy or instability of the cyclopropane ring compared to other rings. Okay, so then the 4-membered ring isn't as bad. You would imagine with a 4-membered ring, you could make a square. The largest angle you could make here would be 90 degrees. Not terrible, not as expanded as the 109 you would hope for. But if you did make a flat ring, let me try to draw it a little differently to make it look like it's coming in and out of the plane of the screen. If I draw where the hydrogens are, they are all eclipsing. This orbital and this orbital are overlapping. If I draw a Newman projection, the hydrogens here on the front carbon are eclipsing the ones on the back carbon. And that would be true for both carbons. So with eclipsing all the way around, and each one of these hydrogen-hydrogen eclipsing interactions making it 4 kilojoules per mole less stable, that is making it pretty unstable. So what this ring will do is avoid being flat. It naturally avoids being flat to avoid some of this torsional strain. The hydrogens on adjacent atoms eclipsing makes it less stable. So you get this kind of puckered shape where this hydrogen is going to be a little bit staggered between these two hydrogens instead of perfectly eclipsing with it. In order to do that, the angle in the ring has to be a little bit less than the preferred 90. That's the maximum you can make. So by sacrificing 2 extra degrees and creating slightly more angle strain, it allows a significant amount of torsional strain to be avoided, and that overall makes the molecule more stable. So why does it adopt this non-flat or puckered conformation? It does that to avoid, so it sacrifices a little bit of angle strain, but it avoids some of the torsional strain associated with the eclipsing hydrogens on adjacent atoms. So take a look at the video with the model on that one. See if you can make the model yourself and see what I'm pointing out in that video to see how making the 4-membered ring so it's not perfectly flat avoids some torsional strain and makes it a little bit more stable than it would be if it were flat, even though if it were flat it would have slightly less angle strain due to the angle being a little bit closer to 109 than reality. The 5-membered ring obviously is more stable. If I had a flat 5-membered ring, the angles would be 108. That's pretty good. Pretty close to 109. The problem with the flat ring, though, is the same problem we just saw with the flat 3 or 4-membered ring. Any flat ring is going to create a situation where the hydrogens are eclipsing all the way around. Eclipsing hydrogens. So the more carbons I have, the more unstable that is, because every pair of hydrogens eclipsing all the way around the ring adds 4 more kilojoules per mole of instability to the structure. So the 5-membered ring is slightly less stable than the 6-membered ring, but it's not nearly as unstable as it would be if it were flat. Even though there'd be very little angle strain in the flat structure because the angle is very close to 109. So in the 5-membered ring, it adopts this envelope shape where you can imagine 4 of the carbons in the same plane, and then the 5th carbon is kind of lifted up above that plane. By doing that, it creates some staggering instead of full eclipsing all the way around like it would be if it was flat. So grab your model sometime, make the 5-membered ring flat, put all the hydrogens on, and see how they're eclipsing all the way around. And then pull one of the carbons up out of the plane from the other carbons and see how it creates some staggering. I showed that in the other video, but you want to look at that yourself as well and make a comparison. If you're not seeing it, bring your model to lab and we can talk about it in person. I can show it to you. But what we're seeing here is this hydrogen here is a little bit staggered. It's not eclipsing this one, it's not eclipsing that one, and and this hydrogen here is staggered between the CH bond and the CC bond there. So there's some staggering, and that allows it to avoid some of the torsional strain. So the same reason that the 4-membered ring adopts this weird non-flat shape, the 5-membered ring adopts the envelope conformation or non-flat conformation to avoid some torsional strain. There's still some torsional strain there, which is why it's not quite as stable as it should be. You've got some hydrogens on the other side where the ring is kind of flat that are eclipsing. And there's no way to avoid that without creating a lot more angle strain. So the angles being relatively close to 109 mean that it's not very unstable, but there's a little bit of torsional strain back there. So that does increase the instability of the structure slightly. So 5-membered rings are pretty common. There's a lot of structures that involve 5-membered rings. They're not that unstable compared to other structures like the 6-membered ring or straight chain structures that don't involve any torsional strain in their lowest energy conformation. So this is a small amount of instability associated with this means that it's not terribly uncommon to find molecules with 5-membered rings. So we'll see it's more of those moving forward. The 6-membered ring is really nice. It has 0 ring strain. Its angles are a perfect 109.5 in its most stable or lowest energy conformation, and there's no torsional strain in its most stable, lowest energy conformation. So it doesn't have either of the two features that normally make a ring unstable. If I made the 6-membered ring look flat, if I made all 6 carbons in the same plane, then I would see a lot of torsional strain. Each pair of hydrogens on adjacent atoms, their electron clouds would be repelling. So a flat 6-membered ring is really quite unstable. Plus, the flat ring would have angles of 120, which would force the carbon-hydrogen-carbon-carbon sigma bonds too close together here at an angle less than 109, and that would make some repulsion there. So to avoid this instability of the torsional strain and angle strain, it adopts what we call a chair structure. And so in the chair structure, you can imagine 4 of the carbons are in the same plane. And then there's 1 carbon that is above that plane and 1 carbon that is below that plane. So these 4 carbons make like the seat of the chair, and then there's like a backrest, and then there's like a footrest. And so if I'm like hanging out here, I can't really put my feet up in this chair, unfortunately, but I can really relax in the chair there. So if hopefully you can see that as a chair. The point of the chair, though, is by taking the flat structure and lifting one of the carbons up to make the headrest and the other far carbon down to make the footrest, it alleviates all of the angle strain and all of the torsional strain. And we can see that here in the chair structure. It's much easier to see in the model. You can see it in the Newman projection. Check out the video, though, where I make a model of that. If you want to look at that in more detail, bring your model to lab and we can talk about it in person. I can clarify it if you're not sure of any part of the video. But what we see here is if we look down this carbon and down this carbon, this is my front carbon. These are the carbons that's directly behind it. This is what my Newman projection would look like. There's no eclipsing. Everything is staggered. There's no hydrogen directly on top of another. And if you work with the model, you'll feel the model relax as you move it into the chair. If you make it flat, there's tension in it because the angles are not optimized. So this hydrogen here, staggered right between the 2 hydrogens on the front carbon. Everything is staggered all the way around. What I do see, though, are some gauche interactions. Right? This CH2 group here is a 60-degree dihedral angle from this one here. And so there is a little bit of instability associated with those groups being a little bit closer together. And we'll see how that translates into something called 1,3 diaxial strain. So it's not as unstable as these 2 types, but it is slightly destabilizing to a ring. And we'll see how that becomes relevant. I think, let's see, is that a topic? Yeah, we're going to talk about that today a little bit. Alternatively, you can make the 6-membered ring into a boat. So we said in the chair, you've got Actually, let me draw that here. In the chair, you've got the head of the chair, and then you've got the feet of the chair. Well, if instead of putting the feet down, if you make another head, then that kind of looks like a boat a little bit. The boat is not very stable because the boat has something called flagpole interactions, and it has some torsional strain. So the angles are still 109, and that's an advantage of the boat. It doesn't have any angle strain, but there is torsional strain. If you look at the model, you can see that some of these hydrogens are eclipsing one another, which we did not have in the chair. We can also see the flagpole interaction. So this hydrogen right here, you can't really see it in the picture here on the slide, but these two hydrogens are actually pretty close together, and their electron clouds repelling makes it relatively unstable there. That's especially clear if you see the model. So make a model of that, mess around with that, and bring it to class and to lab, and I can help you understand why the chair is much more stable than the boat here. Let's just take a look at this Newman projection here. So let's say we were looking down this carbon axis here, and this one here at the same time, right? Our eyes over here, we're looking in that direction. I guess I'll draw it up here where there's a little bit of space. So we'll call this carbon 1 and 2, and this 3 and 4. Right? So if I'm looking from this direction, I have carbon 1 directly in front of carbon 2, and I have separately carbon 3 directly in front of carbon 4. Carbon 1 and 3 have this extra carbon bridging them, and so that would be connecting the two front carbons. And then carbon 2 and 4 have the same thing. It's coming up, bridging the two back carbons. So I'm already seeing eclipsing there. There's some eclipsing between the groups coming off of carbon 1 and carbon 2 there. And if I look at the other hydrogens, I see the same thing. Carbon 1 has a hydrogen coming down. Carbon 1 has a hydrogen coming down, and then one out to the side. And so does carbon 2, straight down and out to the side. So there's some torsional strain there associated with that eclipsing. And that's true on both sides, where I would draw my Newman projection. So the boat has a lot of torsional strain associated with it. It's easier to see in the Newman projection than in this structure over here. And that makes it significantly less stable, in addition to the hydrogens that would both be on these two atoms pointing toward one another, creating some repulsion as well. That's the flagpole interaction. Right? Flagpole interaction is not torsional strain, because the two hydrogens with their clouds coming close together are not on adjacent carbons. So it's something a little bit different from torsional strain. It's just more generally repelling electron groups, which is called steric hindrance or steric strain. So here are the energy differences between the much more stable chair and the less stable boat. If any part of the ring gets flat, it becomes much less stable. Making the entire ring flat would make it even more unstable. This twist boat is not something we usually talk about. It has a little angle strain, but it avoids some of the torsional strain that we just saw in the boat. In order to get from the chair to the other chair, which we'll see in a minute, you've got to go through these other higher energy states though. Right, so what are we talking about here? We're talking about going from the more stable chair where everything's staggered, there's no torsional strain, all the angles are right. We're going to lift the feet of the chair up a little bit till that part of the structure is flat. That makes it way less stable because the angles get distorted over here and there becomes some torsional strain between the hydrogens attached on those carbons. So then if I lift it up a little bit further, I can go to the boat, which is a little bit more stable. And then as I start to bring down what was the head of the chair, to become flat, it becomes way less stable again. And then when I bring it down a little bit more, I create another chair. So these two chair versions might look the same, and they are equal in energy, very similar. But once I put a substituent on the ring, as we're about to see, there is a difference between one chair and another chair. So you really want to work with the model here and get some experience with that. Bring it to lab. We can look at some examples together and talk about this in detail. But there's a significant difference between the stability of a chair when I have a substituent attached in one version versus flipping the feet up and then flipping the head down here to get to another rotated version of the chair. Right? So these two chair versions are what the molecule is going to look like nearly all of the time. And if one's more stable than the other, it's going to actually determine what the real structure looks like. And so that's what we want to get into a little bit moving forward. So to draw a chair, it's actually 3 sets of parallel lines, and the book does a really good job of explaining that. So I would walk through that section in the book. When you draw a chair, the things that are substituents that are attached to the chair, 6 of them will be pointing straight up from the points between lines that intersect in an upward direction. And then 3 of the 6 groups are going to be pointing straight down from the points where lines intersect pointing downward. Right, so you want to make sure you get that straight. This is not correct. If 2 lines are intersecting at a downward point, I don't want a thing coming straight up from there. It should be coming straight down. If 2 lines are intersecting from the chair in an upward direction, I shouldn't have a substituent pointing straight down. It should be pointing straight up. Those are called axial groups. The axial groups point straight up off the top parts of the chair and straight down from the bottom parts. There's also positions called equatorial positions, and when I draw my chair, there are 6 of those. So every carbon on the ring has an axial group, and every carbon on the ring has an equatorial group. If those are all hydrogens, that would just be cyclohexane, but other substituents can be connected there to any one of these positions connected to the ring. So practice drawing chairs, practice getting these things drawn at the right angles. It's really important that you don't do stuff like this. So if I have a chair, the backbone of my chair drawn, and I want to show what's connected to this carbon, since the other 2 carbons have angled their bonds up to it, that means the axial group is pointing straight up and the equatorial group is coming down at an angle. I always have one group coming up and one group coming down. Sometimes that group's coming straight up, sometimes it's coming up at an angle. The group coming down might be coming straight down, or might be coming down at an angle. So I really have to get used to drawing these things correctly. So any carbon where the other carbon's bonds are coming kind of up toward it, the axial group's pointing straight up and the equatorial group's coming down at an angle. That's true here, down at an angle, and here, down at an angle. Any of the groups, or any of the carbons on my chair, oh, that's not a very good chair. Try that one again. Any of the carbons of my chair that have the bonds pointing down, the axial group will be pointing straight down and the equatorial group will be coming up at an angle. So straight down, up at an angle, straight down, up at an angle. So there's 12 groups attached to a chair, and you want to make sure you draw your chairs with them pointing in the proper direction in space. Otherwise, you won't be correct with your work. So you want to practice that a fair amount. Alright, so let's talk about flipping chairs. So here I've got a chair, I've got one substituent. And I also made a video to show this flipping. So when we talk about flipping a chair, we're not talking about flipping it over like a pancake, right? You cook a pancake, one side gets done, you flip it over and cook the other side. That's not what we're talking about here. We're not talking about just taking this molecule and flipping it over. What we're talking about are rotating the carbon-carbon single bonds, not flipping the whole structure over. So I find the foot of the chair, I find the head of the chair. I rotate these carbon-carbon bonds to put the head down. That makes a boat temporarily, or at least like an upside down boat. Then I take the feet of the chair, I'm rotating these carbon-carbon bonds, and I rotate that up. So the foot becomes the head, and the head becomes the foot. When I do that, any group that's positioned in an axial position will become equatorial, and vice versa. Right? So if I had this chair here, maybe I've got an equatorial group of atoms there. If I do the flip and I flip this down and then I flip this up, now the head is on this side. Didn't draw very good. Let me try that one more time. There we go. So now, if I number these, just to keep straight what's what, carbon 1 has moved up and now it has become the head. 2 and 3 don't really move much. 4 was the head, it now comes down to become the foot of the chair. 5 and 6 don't move much. So my group was on carbon 2, it was pointing down and at an angle. If I do this flip, it will be coming straight down. Didn't draw that very straight. So the equatorial group becomes the axial group. Why does it matter whether a group's equatorial or axial? It matters because there's a difference in stability, which we'll see in a minute. So I need some energy to do this because temporarily it has to go through these unstable states to get from one flipped version of the chair to the other. Probably easier to see with a model than looking at these Newman projections, so I usually don't spend a lot of time on those. I'm not gonna ask you to draw probably a Newman projection for a cyclohexane. So let's take a look at a specific example. So here we've got a chair, we've got a methyl group pointing up. When I do a chair flip, an up group stays up. A down group stays down. Right, so this is coming straight up. When I flip the head of the chair down and the feet up, it's still up. It's not going to be straight up anymore, but it's now up at an angle. This one is axial, this one is equatorial. And if I look at the difference between these two, I can see this one is much more stable. I don't get a 50-50 mixture. Why is this one more stable? Why is an equatorial position more stable for a group than an axial position, with very few exceptions? Well, there's got to be some type of repulsion that this is creating. And we can see that if we look at the other axial groups that are pointing straight up. And this is especially easier to see on the model, and if you look at the video it might be more clear for you. But any axial groups on the same side of the ring are a little bit too close together. It's the equivalent of being gauche. Their electron clouds become close enough together to repel significantly. And I can see, especially in the model, when a group's equatorial, it's kind of pointing out from the ring. Everything else over here, there's really nothing close to this that's going to interfere with this electron cloud, or no other full electron clouds coming close to the methyl group to repel it if it's in an equatorial position. So even though this can flip back and forth, as long as there's enough energy to get over the activation energy barrier where we had the boat and the half chair that was less stable, this version where my electron group is in an equatorial position should be more stable than the axial one. And so this hopefully illustrates the same thing. If that group is in an axial position, its electron cloud is going to be close to these hydrogens. If I had multiple big electron clouds in axial positions on the same side of the ring, that would be really unstable. If I have large groups on the bottom side of the ring, those groups also crowd one another out. The equatorial groups, those are kind of pointing out into space. They're not really that close together. They're gouged to one another, but this one, this axial group repulsion, especially if you make a model, you'll see these groups are pretty close together and they cause a lot of repulsion. And so that's called 1,3 diaxial strain. So if I number my carbons 1, 2, 3, the axial groups that are on carbon 1 and 3, or if I number the other way around, 1, 2, 3, axial groups are always on carbons 1 and 3 with respect to one another to be on the same side of the ring and to cause this type of repulsion or strain. So that's what we call 1,3 diaxial strain. And so that makes the molecule significantly less stable than it would be. And those axial groups are gouged to other parts of the ring. The other hydrogens on those groups that are gouged to the axial groups create the instability. The equatorial groups are actually anti to other parts of the ring, and so they don't have that same degree of instability. If the group is an especially large group with lots of crowding, it's going to be even more unstable if I put it in the axial position and create 1,3 diaxial strain. So if you're looking at structures that have different substituents, you always want the most, I should say that you want the biggest electron cloud to avoid the axial position. Unless I'm asking you to draw the most unstable version of a structure, you always want to flip the ring until the biggest group, especially if you have multiple groups on the ring, is in an equatorial rather than an axial position. So next time, when we pick up on Thursday, we'll talk about what happens if I have multiple substituents, like 2 or more substituents on the ring. How can that ring be flipped to create the most stable and least stable versions of that chair structure? Any questions about anything from today? I know there was a lot. We kind of went over time a little bit here, but there's a lot for you to practice there moving into your exams starting next Tuesday. So please let me know if you have questions about those. If you're doing work and you're finding that your answers are matching up well with the solutions guide, that's great. If your answers are not, but what's in the solutions guide makes sense to you and allows you to fix your answers and you understand them well, that's great. But you really need to get to the point where you can independently solve correctly a lot of these problems if you expect to be able to do the exam problems correctly, obviously. So please practice up and let me know if there's concepts or issues that aren't quite making sense when you're looking at the solutions guide, or during lab if your group is in good shape and you're not behind and you want to just take some time and talk about some of these with some models or on the board. Please let me know. We can always talk about lecture concepts a little bit because we do have a good deal of lab time. It's been working out great for everyone to get done what they need to get done so far. So on Thursday we're going to finish up chapter 4 here with a little talking more about chairs and situations where my chair has more than one substituent attached to it. And then we're going to get into chapter 5, which is about looking at structures where spatial positioning of atoms changes the identity of the structure. And that's going to get very visual as well. So I made some videos for day 10. If you want to look at the videos that I specifically made for some of the structures on the slide from today, those are on Canvas, listed under day 9. And there's some for day 10 if you want to look at those before we do the day 10 lecture. That might help with the quiz questions or with what we're talking about when we have that lecture. So I'm going to stay on a little while. If anyone has any questions, feel free to speak up or message me in the lecture text channel.